Okay, let me just minimize this. Okay, so thank you everyone for coming for my PhD seminar. I'm talking today about autonomous classification under uncertainty. This is, of course, my PhD seminar. I'm Vadim Indelman and supervised by Associate Professor Vadim Indelman. So let us begin. First of all, some introduction. Object classification is an important problem in computer vision for wide applications such as autonomous vehicles, UAV, in terms of environment perception. In recent years, there were notable advancement within the field of classification with the introduction of deep neural networks. They are far more advanced than everything that was before that. But still, reliable classification is still a difficult problem, and it is remaining a challenge. In particular, we have multiple factors that affect classification accuracy, such as the lighting in the environment, occlusion, some objects are occluded, the image resolution with low resolution is more problematic, and two additional factors that we will address here more in detail. This is viewpoint dependency, that an object might look different and hard to identify from different viewpoints, and classifier epistemic uncertainty. When the test data, the classifier must be trained. So when the test data does not match the classifier training set. So specifically, when we're talking about the viewpoint dependency, we also want to go into a short introduction for SLAM. What is SLAM? Basically, this is the following problem: that given some measurements, we need to construct a map of the environment and infer the robot's pose. In more technical term, in classical SLAM, we aim to maintain the following posterior distribution, in which we have the probability over robot poses, object poses, we have the measurement history and the action history. Using some mathematical formulation, base rule and the chain rule, we can reach the following expression, in which we have in blue here the pose priors. We have in green we have the motion model, and in yellow we have the measurement likelihood. And within the measurement likelihood, there also comes the question of data association. We want to associate between the measurements that we get and the objects. This is by itself a pretty significant problem that we must address. And if this entire probability is Gaussian, then its parameters can be computed via methods that already exist in the literature, such as ISM2. So the presentation will have the following structure in here. We divide it into 4 sections. The first 2 sections deal with the localization uncertainty and viewpoint dependency. The third section deals with epistemic uncertainty, and the 4th section we both propose an approach that deals with viewpoint dependency and epistemic uncertainty, and also expand it to active formulation. So let us begin with the first work. The setting is as follows. Our setting is what's called a semantic SLAM or object-based SLAM. This is a SLAM which we get from the object some measurements, and we want using this object to construct an environment. In this setting, the robot observes objects, and it receives first of all geometric measurements. For example, you can use radian bearing, and semantic measurements of class probability vectors. Our key challenges here that we must address are as follows. First of all, we have classification aliasing. That means an object from different viewpoints may appear in such a way that the class can't be easily discerned. So it may appear like several different classes. And also data association aliasing, that the environment that the robot looks at can be a few different environments, as can be seen on the example here on the right. we have images of corridors. Those are actually two different corridors, but the corridors looks practically almost the same. So we aim to maintain the following hybrid belief. We have the probability over robot and object poses. We have the object classes, and in beta, this is the data association realization, the entire realization for the beginning of time, and this is given a measurement and action history. We denote this as this curly H. Our contribution, we will formulate them as follows. We present an approach that maintains a hybrid belief over continuous and discrete random variables. The continuous are robot and object poses. The discrete are object classes and data association hypotheses. And we address the coupling between classification and slab problem via a viewpoint-dependent classifier model. We're leveraging the coupling between the poses and classes to, first of all, assist in data association disambiguation, and to improve in classification localization performances. And when we compare to previous works thus far, they first of all either consider the most likely class semantic measurements instead of a probability vector like we do, and when they do utilize the viewpoint-dependent classifier model, they did it with solved data association. This work was published and presented in the conference IROS 2019. So the assumptions that are used here, we have a single robot observing and moving within a static environment. We have a known number of objects, and we have a Gaussian motion model, geometric model, and classifier model, which we'll detail in the next slide. And we also what's called the object observation model that attempts to predict whether given some poses, will we actually see the object or not, as is seen on the right. We have two objects, one is seen, one is predicted to be seen, and one is not. So the probability for the object to be seen is some constant, and the probability, and for the other object, the probability of this association is 0. Now I will discuss the classifier model. The semantic measurements are viewpoint dependent. We use probability vectors, and you can see on the illustration on the right, we have a SUV that we observe for multiple angles, and from each angle we get different probability vector. Even if, for example, the class 2 is the SUV class, if it even correctly identifies the current class. This model is assumed Gaussian with parameters that are dependent on the object class and the relative pose. This is especially in purple. This is important. This is what's the coupling between classes and object poses is. The approach that we take is as following. We split the hybrid belief into continuous and discrete parts, which we have the B, C, beta is the continuous conditional belief of given some class and data association realization. The parameters of this belief can be inferred like in standard SLAM with optimization methods such as ISM2. And W is the weight of this belief computed separately for each realization of classes and the data association. The continuous and discrete weights are updated separately as follows. We have the continuous belief is updated using the prior updated using the motion model and the measurement likelihood, and the weight is updated in a recursive form with the following integral, where we marginalize over poses and also include the continuous belief within it. As such, because the measurement likelihood is the measurement likelihood appears in both terms, so the classifier model affects both the continuous weight update and the discrete weight update. One issue that we may run here is that the number of realization may go exponentially. So first of all, many realization, the observation model predicts that we won't see the objects here. So with many weights, the weight is 0, and we also do some pruning. pruning for pruning the small weights and keep the number of realizations small. Some simulation results in here. We compare between cases without and with classifier model. Without on the left, with on the right. We have pose estimations for the robot. The ellipses represent the pose estimation, and the thickness of the ellipse represent the weight of the realization. You can see that that when we don't use the classifier model, what happens is that we have many possible data association realizations. It's for the algorithm, it's hard to discern what's going on here. And on the right, we get fewer realizations, and also the we want actually the ground truth here to be at the time k equals 1, and we see here that the estimation is much closer, and there are much fewer realizations. Now, when we take to time k equals 15, we can see the same behavior, similar behavior, that when we don't use the classifier model, we have many different realizations. This is split in two. And when we do use the classifier model, there is only a single realization with more accurate localization. Here we display the probability vector for the realization of classes and data associations, and we compare between with classifier and with that classifier. And we can see eventually that there are fewer belief components in here, and we can see that there is a stronger disambiguation. And also with the ground truth hypothesis, we can see that using the classifier model, we get the true realization with the classifier model with much higher probability. So after presenting an approach for a single robot, there comes the question that what happens if we can't actually observe the entire environment using a single robot? So what we propose here is an approach that expands this hybrid belief maintenance into a multi-robot distributed setting. So the setting is follows. Now we have multi-robots observing the objects within the environment. Each one is autonomous. Each one is, not autonomous, but independent. And they also get the geometric measurements for each and every object, and they also get the semantic measurements. Our key challenges is classification aliasing, like was presented in the previous section. And second of all is estimation consistency. This is something specific for distributed multi-robot settings. To focus our contribution here, the data association now is assumed to be solved, and eventually we aim to maintain the joint hybrid belief. Now with robot and object poses in X, in C as object classes, we have the history of measurements and actions in H, and we also have a superscript that denotes which robot, the robot group or the single robot that this hybrid belief refers to. Formulate a contribution. We present a multi-robot approach, distributed multi-robot approach that maintains a hybrid belief over robot and object poses and also object classes. We address the coupling between classification and slab problem via viewpoint-dependent classifier model, as in previous section. And we also address estimation consistency for continuous random variables and discrete random variables. And compared to previous works, usually in multi-robot setting don't deal actually with semantic information, and as such they only address double counting for continuous variables. This work was presented in IROS 2020 and published in RAL 2020. So let us begin to describe here. First of all, some introduction of what double counting means. In distributed systems, in multi-robot distributed systems, a measurement should be counted no more than once. And when information is relayed between robots, we risk actually double counting. So what happens if there is double counting? Double counting lead to overconfident estimations, with covariance matrices that are much smaller than in reality. And also this is problematic if the measurement that we get leads to erroneous estimation. We have here the simple example when we consider random variable C with two data sets in which the two have an overlapping measurement. Then the posterior must include this red denominator to actually avoid double counting. And without this denominator, which happens a lot in SLAM, this measurement is double counted. And what eventually happens is can you actually mute the 1 second. Okay, thank you. So double counting pushes posterior to extremes. You can see in the illustration on the right, which we in A we have the semantic measurement counted only once, and B counted twice, and C counted 3 times. So it pushes it to extremes, either 0 or 1. The general approach is as follows. Each robot maintains 2 separate hybrid beliefs. First of all, its own hybrid belief, divided into continuous and discrete parts, like showed in the previous section, and a joint hybrid belief from all the measurements that it gets. Each robot actually maintains a stack of individual beliefs that it has, and it sends between the other robots all the individual beliefs here. So on the example on the right, we have a free robot system. The variables that are kept are object pose marginals and object class marginals, and also a timestamp. The timestamp is used to determine whether the information that the receiving robot has needs to be updated. If the information is updated, then the old information is removed, and thus the joint estimation is consistent, and we avoid double counting. Now we want to show some experimental results. In this scenario, we have 3 robots communicating in the environment with 6 identical chairs with different orientations. We have 3 candidate classes and trained classifier models, and we compare between 3 cases. We have a single robot, distributed, and with double counting. For a classification benchmark, we use a metric called MSDE, mean square distance error. And this metric, the advantage of using this metric is when the classification for one object is completely correct. MSDE doesn't go to infinity, and we have more information like that. Briefly going over the important notations for the SLAM graph, we have on the top left, we have the robot communication graph representing which robots communicating with which. We also have a object pose estimation with the gray ellipse. We have the robot estimations with the red ellipse, and we also have a gray line that represents which objects the robot observes at current time. And we show also a class probability graph notations. This is a bar representing the probability of classes. For class 1 probability, we have a blue color, orange color for class 2, and white for class 3. And in all cases, class 1 is ground truth, so we want everything actually look blue. It's pretty simple like that. And here we want to show some movie of our results. Let's see. This is here. Okay. First of all, we show for a single robot without communication. You eventually the robots is the left one is robot 1, the middle is robot 2, and the right one is robot 3. If you focus especially for robot 2, you notice that there are errors in the classification, and eventually there are also many class hypotheses that leads to different pose estimation. This is without communicating, and the coverage is also not completely full here. So let him finish this scenario. Okay, and in the distributed, the robots do communicate between each other, and you eventually will see that even when there are erroneous classification scores, eventually the communication allows the robots to fix their estimation, and also the graph which is complete of all the objects. Now, especially when the robots communicate between each other, you can see that they have very similar class probabilities, and eventually the estimation, of course, is more accurate here. Okay. Finally, some graph. This is for estimation, pose estimation accuracy. You can see that in general the distributed settings show more accuracy. This is the covariance. The covariance for distributed is a bit lower, no communication. And MSDE, you can see that eventually the blue one is the best one. MSDE, the lower we can get, the better it is. So this was the experiment presentation. So we reach somewhere around the middle. So I want to do a quick summary. We present an approach for semantic SLAM that maintains hybrid belief over robot and object poses and object classes. First of all, we addressed a single robot approach that assists in data association disambiguation, and the approach eventually was expanded to a multi-robot distributed setting. We leverage the coupling between poses and classes via a viewpoint-dependent classifier model, and for the distributed setting, we avoided double counting for both continuous and discrete random variables. So now, I want to continue to the part where I talk about epistemic uncertainty. Okay. First of all, some introduction of what's going on. The classifier has to be trained on some data set, on some set of examples, but this training set is limited. Even with giant companies, the training set is still not encompassing everything. And during test time, we may encounter data that is outside the classifier training set, and classification scores are unreliable. They can be pretty much everything, and for this, and what happens, that results might be catastrophic. As we can see on the right, it was a case when autonomous vehicle crashed into a side of a truck that it identified incorrectly as a sky. So the question that comes here is, can we reason about how certain classification scoring is? I want to quickly introduce notations that we will use in the following slides. We have the class probability vector. This is the probability. This is the probability of the class given some image and W. This is the classifier weights, and this is a probability vector. This probability vector can be represented either as a bar graph on the right, or more to the right as a point within a simplex. In this case, this is a 3D simplex. And we also want to introduce the posterior class probability. This is lambda. This is given a series of class probabilities. This is class probability by itself, and also can be represented as a bar graph or a point within the simplex. We use what's called for classification a convolutional neural network. It gets an image and eventually outputs in a class probability vector. The classifier parameters are weight realization, are trained from labeled dataset example T. This is what's called this is what's called a supervised learning. And given fixed weight, this is what happens usually. The classifier output is deterministic. Okay, so how do we actually reason about epistemic uncertainty? We use a method called MC dropout. So basically, what dropout does? Dropout modifies the weights by randomly turning off neurons, and this is approximate the probability of the weights given training data set. And how do we use it? We run multiple instances of this dropout. Different neurons are turned off, and we get multiple probability vector points, multiple gamma points corresponding to the weights, and they also approximate the probability of P of gamma given some image and training data set. And the epistemic uncertainty, we ask ourselves how close the image is to the training set. So the idea is, if the epistemic uncertainty is large, then these gamma points will be very spread out, and vice versa. If the epistemic uncertainty is small, they will be concentrated in a single spot. As a side note, I must note that this work does use MC dropout, but it can also utilize other epistemic uncertainty aware classifiers, such as those that created by bootstrapping, for example. Eventually, we aim to maintain the probability over the posterior class probability, this P of lambda, because all gamma, as we established, are random variables, so is lambda as well. And this P of lambda and also P of gamma actually may describe several cases. First of all, is out of distribution case. It's where the classifier gets data that wasn't trained on entirely, and the expectation here is somewhere in the middle, and the distribution is very spread out. BID is the case of high data uncertainty, when it gets data that the classifier was trained on, but from that data the classifier can't identify which class the data belong to. So this is presented with a concentrated distribution in the middle. C is the confident prediction. This is the ideal scenario that we strive for. Is that when the expectation over lambda is somewhere near the edges, it means that it identified some classes, and also the uncertainty is small. And D is unconfident prediction. This is somewhere in the middle, where the expectation is somewhere close to the edge, but the uncertainty is still large. So the contribution of this specific work is, first of all, we present a sequential classification method for maintaining this probability of lambda. And thus, we reason about posterior epistemic uncertainty given the data thus far, compared to previous works up to that point, that the sequential classification method only reason about maintaining the posterior itself, instead of the probability over the posterior. And works that do infer epistemic uncertainty for classification do it only on a single image basis instead of sequential, like we do. This work was actually the first chronologically. It was presented in iOS 18 and published in RAL 18. So let's go over our assumptions. We have a singular object observed multiple times. This is a simplified scenario. We have a classifier output of a cloud of gammas that approximate the probability of P of gamma given image and a training data set. This is compared to a usual classifier that does only a single gamma. And we have an informative prior for the classes, and we also have Dirichlet distributed non-viewpoint dependent classifier models. Those can be, for example, for free classes, represented as free simplices. The approach that we take is the particle-based approach, using the base rule for each class. For each class, we can update the prior lambda using the measurements that we get that go through the classifier model. So the process goes as follows. We have a previous data in a form of point cloud. We have new measurements as a form of point cloud. Each measurement is projected to a different point in the point cloud, and we multiply all pairs. And we have to do some sampling here, and we get the current data. The subsampling is necessary to reduce computational effort and not deal with gigantic number of points. Here I want to illustrate how does this approach work. on the top case, we can see a case in which the uncertainty decreases. This is a case that is actually what do we want. We have this prior on the left, lambda k minus 1. We have a new measurement of cloud of gamma k, and each measurement is projected to a new point within the simplex. And multiplying everything and normalizing, we get the posterior L gamma k, which is concentrated near the corner, and the uncertainty here is low. There can be also case which posterior uncertainty increase. This is compared, for example, for a classic SLAM problems when the uncertainty only decreases there. So it's when we have some prior and we have measurements that actually don't agree with set prior. When the measurements don't agree with set prior, we can get a case in which you can see on the posterior on the bottom right, the points are very spread out, so you have a lot of uncertainty here. For this work, we want to show some experimental results here. We photographed an object multiple times and corrupted the images with occlusions, blur, different color filters. We have 3 candidate classes. Class 1 is correct, and we compare the following approaches in here. First of all, the class probability posterior P of C given gamma with no classifier model. The same with classifier model, and our approaches when we consider all pairs and when we consider subsampling. Here are the results. On the top left, you can see the approach without the classifier model. We flat out get the incorrect class. We want to see the blue to be the top one. On the top right, we can see this approach with classifier model. We do actually get the correct prediction for the class most of the time, but you can see here it's very jumpy. It can if we like consider the incorrect time, then we may get very erroneous classification results. On the bottom left, we can see our approach with the class expectation of our approach. We can see that after the first image, the class probability of class 1 is the highest, and it keeps the highest even if there are measurements contradicting. And on the right, you can see the standard deviation, and which is actually representative of the model uncertainty. So it opens up a possibility to reason about model uncertainty. The last thing that I want to mention here is that using the results for subsampling and using all points, we get similar results, so we can safely use subsampling here without fear that we get incorrect classification results. So a summary thus far for this work, we propose maintaining the distribution over the posterior class probability for classification and extracting epistemic uncertainty. We utilized a cloud of class probability vector as a classifier output instead of a single class probability vector like previously. To reduce computational effort, we proposed using a simple subsampling method, and we showed superior results to commonly used approaches for classification as well for presenting epistemic uncertainty. So, going to our last section, we combine here both viewpoint dependency, localization uncertainty, and epistemic uncertainty, and eventually go to planning. So up to this point, we presented methods for addressing viewpoint dependency of classification scores, localization, mapping, uncertainty. These are the first two methods. And classifying epistemic uncertainty, then this was the first method that we mentioned. Now we introduced two methods that address both viewpoint dependency and epistemic uncertainty in inference. The first one is called multi-hybrid, MH, and the second one called joint lambda pose. This is JLP. And this formulation eventually we extend to belief space planning. So to formalize a contribution, we maintain an epistemic uncertainty aware joint belief over poses and class probabilities. MH and JLP, as we mentioned. We utilize a viewpoint-dependent classifier uncertainty model. We will go over what it is to predict, first of all, epistemic uncertainty given viewpoint. improve classification performance in inference, and generate predicted measurements for belief space planning. And finally, propose a information theoretic reward over posterior epistemic uncertainty. While in previous work, first of all, they don't consider classifier epistemic uncertainty for belief space planning. And the work that does consider epistemic uncertainty aware planning, it did so with solved localization. This is a ongoing work for a paper that very soon is going to be submitted. So let us first of all present go over a brief introduction. What is actually belief space planning? Belief space planning is an extension for classical SLAM for planning under uncertainty. We have some would say animal called objective function that we say that given belief is a probability of random variables given measurement in action history, and the proposed action sequence, we can reason about the following objective function. This objective function is commonly used. This is the expectation of a future rewards. This objective function can be rewritten in a recursive form as follows, in the middle section, the yellow section here, is the future measurement likelihood term, and this term is used to generate future predicted measurements for planning. The eventual aim of belief space planning is to find the optimal action sequence such as it maximizes this objective function. It specifically maximizes because the objective function is a form of rewards. For us, the key issue will be here is generating predicted semantic measurements with epistemic uncertainty. So we have two possible options. The first of all is generating raw images, but this is a high dimensional problem. Actually, generating an image, the output is very high dimensional. And while it was done actually previously, there are work that actually do that. They only do that in very specifically trained environments. What we propose instead is generating it directly from the classifier model itself, in which the output dimension is much smaller. It would be a probability vector, and we can be possibly generalized to more environments. So first of all, we go over classifier uncertainty model. We require it to satisfy a few conditions, few requirements. The first requirement is that it must fit within the inference framework. So the Dirichlet classifier model that we showed previously doesn't fit us because it doesn't go well with Gaussian distributions. And for planning, the Gaussian distributed classifier model doesn't fit us because the sampling from a Gaussian distribution doesn't gives us probability vectors. So what we do here is actually say that this gamma k is logistical Gaussian distributed. So logistical Gaussian distributed, and the inference is performed over the L gamma k. L gamma k is the logit transformation of gamma k, looks as follows. And here the support for this L gamma k will be from -infinity to infinity. This is also applied to L lambda eventually, as we'll see in the future. The model training set is a tuple of relative pose and the accompanying point cloud. We can see on the right we show the classifier model for both example of classifier model for both gamma space and L gamma space. You can see L goes from 5 to -5, and gamma space have to stay as a probability vector. And eventually, this model is predicting epistemic uncertainty. The first method we want to show is MH, multi-hybrid. We aim to infer the joint belief over lambda and poses. And how we do so? We do so by fixing weight realizations. We have a certain number of fixed weight realization, and by marginalize over this W, the weight realizations, the right-hand side in the middle equation can be inferred by maintaining a hybrid belief per each W. This is actually maintaining multiple hybrid beliefs. On the right, it can be represented as a form of a factor graph. For this actually we show this for a single W, but we have factor graphs like that for every W, so it's many factor graphs. In planning, the predicted measurements are generated via classifier uncertainty model, as we showed, and the problem with MH that is very computationally efficient, many realizations. Therefore, we have a motivation to propose an alternative approach, and we propose JLP. The advantage here of JLP is that it maintains, instead of multiple hybrid beliefs, it maintains a single continuous belief that we only need to optimize only over it once. And the belief that we actually aim to maintain is the belief of L lambda. L is the, to remind you, the logistical Gaussian transformation, and the poses. This can be a Gaussian belief, and we have the recursive formulation in which everything in here is pretty much standard, except for the blue part. The blue part is a novel factor that we call JLP factor. And as a side note, JLP is more efficient than MH, even when we consider a multiple object. This is in terms of computational complexity. On the right, we can see an example for a factor graph. On the top and on the bottom, we have these factors that there are 4 lines going through it. Those are the JLP factors, and this is how it's represented in here. The JLP factor, what do we pay here to get this more computational efficiency? We need to have a condition in which JLP factor is actually Gaussian. So if we recall the classifier uncertainty model, which we have the parameters for expectation and covariance, if for all classes and relative poses the covariance matrices are equal between the classifier models, then the JLP factor is exactly Gaussian. But in practice, even if the conditions don't apply, JLP still works pretty well, and the JLP factor is approximately Gaussian. Besides some extreme case where the covariance matrices are very different from each other. Now we go over measurement generation for JLP. Specifically for JLP, the objective function takes the following form. In red, we can see the difference compared to the introduction for belief space planning. We have on the left and on the right, we have the belief, and in the middle, we have the actual measurements that we consider. We have the expectation of the L gamma, and we have the covariance of the L gamma, and the geometric measurements. For sampling the measurements, the geometric is sampled for the measurement model, and the semantic from the parameters of the classifier uncertainty model, compared to MH, where it's sampled, where multiple L gammas are sampled for the classifier uncertainty model. This allows for JLP for more elegant solution for creating measurements, and all the sample measurements are used to infer the predicted future belief. Something that still need to go over is the reward function. Maintaining this joint belief B of lambda in X or B of L lambda in X allows us access to different form of reward function. It can be reward over X, for example, distance to go. Reward over the belief of X, for example, information theoretic costs for poses, using for example the determinant of the pose estimation. And there are also rewards over the expectation of lambda. This is a reward over discrete random variable. For example, we can use information entropy in here. And reward of the belief of lambda, this is a novel reward function type. This is planning directly over epistemic uncertainty. The posterior epistemic uncertainty affects all these rewards, at least implicitly. For the 4th type, we use the negative differential entropy as a reward. We have here in purple the expression for it, and this this minus entropy accounts for both the classification scores with expectation over lambda and sigma over lambda, which represents the epistemic uncertainty without hyperparameter tuning. So for this work, we want to show some simulation results. We have 9 objects within 2D environment. We have 2 candidate classes and motion primitives. On the top right, we have a representation of the classifier uncertainty model from relative poses, from relative orientation of 0 and 360. We have the lowest epistemic uncertainty, and 180 we have the higher epistemic uncertainty. The ground truth of how the objects are laid out can be seen on the bottom left, with the cone representing the areas with the lowest epistemic uncertainty, and the motion primitives are represented on the bottom right, with the red triangles representing the vision cones. What we compare here, first of all, we plan using two types of reward. The first reward is the minus differential entropy. This is the fourth type of reward, capped by some constant to encourage exploration. And the second reward is the information entropy over the expectation over lambda. And we compare between MH, JLP, and an approach that isn't actually utilizing epistemic uncertainty. We call here WU. As in the semantic SLAM multi-robot, we use MSD as a classification benchmark. So here are trajectory examples for planning. Planning over, you can see that the most important thing to see here is planning over R1. The robot passes at least close to all the areas with the lower epistemic uncertainty. This is compared to planning over R2 in the middle and WU on the right, which misses view of these areas, the highly sensitive areas. We show here graphs for the entropy, the sum of the entropy for using MH and JLP. For MH on the left, we can see planning over R1 gives us lower entropy. This is a clear advantage. This also represents the epistemic uncertainty, while on the right is not as clear, but still there is advantage for planning over R1 in here most of the time. The MSD represent classification accuracy. You can see that WU is significantly outmatched by our algorithms, the planning over R1 and R2. We can also see that both for MH and JLP, planning over R1 is better than planning over R2. Of course, MSD, the lower the better. Here we show class probability for all the objects at time k equals 20. Basically, here we show the probability of the ground truth class. So the higher the bar, the better. First of all, when looking at WU without considering model uncertainty, we can see that the results tend to go to the extremes, either completely correct classification or completely incorrect classification. And less so if we use our approaches. The black line represents actually the epistemic uncertainty. There is a slight advantage both for MH and JLP for planning over R1. Here we show the computational time in our machine. This is for MH with 10 beliefs with horizon of 10, so this is pretty long computational times. We can see that first of all, JLP significantly outmatches MH in terms of computational time. W is better, but JLP allows us access to epistemic model uncertainty, of course. This is statistical study when we actually randomize our measurements. We can see on the left, this is the entropy. This is represent the epistemic uncertainty. Planning over R1 eventually is better than planning over R2. And on the right, we can see the MSDE results, where planning over R1 and R2 significantly outmatches planning without considering epistemic uncertainty. And planning over R1 is actually better. So So to summarize this entire presentation, we reasoned about uncertainties in object classification. We reasoned about viewpoint dependency. We presented semantic selection approach that maintains hybrid belief over poses and classes and expanded this approach to a multi-robot setting. We leveraged the couple between poses and classes via a viewpoint-dependent classifier model. And for epistemic uncertainty, we presented an approach that maintains a distribution over posterior class probability. And eventually, we proposed MH and the faster JLP to reason about both viewpoint dependency and epistemic uncertainty, and expanded those two approaches for belief space planning. And for everyone, we used the viewpoint-dependent classifier uncertainty model, both for inference and belief space planning. And our approaches showed increased performance for classification, localization, and data association disambiguation. So thank you everyone for tuning in and listening. And questions?
Thank you, Vladimir. We have time for questions. Any questions? Okay. So if there are not any questions, no questions, I'd like to thank Vladimir again.
Thank you.
Thank you.